So hence safe in shear. So let us move on to the next step, that is check for web buckling. Okay, check for web buckling. Okay, so here from page number 67 we are having one formula. Okay, page number 67. So this is the formula we are going to use. Okay, B1N1 into TW into FCD, design compressive stress. Okay, so if we are going to multiply with, then automatically we can get the value. For here, uh, they have given us using curve C, that is buckling class C. We are going to use it. Okay, so with respect to these values, okay, now we have to refer table 9, which is nothing but from page number 42. Okay, so here we can have for full built up member, the buckling class is about C. Okay, so with respect to C, we have to calculate the design compressive stress. For that, KL by R minimum value needed, that is lambda W. Okay, na? And yield stress, we know that if we calculate this yield stress and that lambda value, then we can calculate the design compressive stress value. Okay, if I'm going to multiply the design compressive stress with that formula, whatever we have given, B1 plus N1 into TW. Okay, now we can get the value of FW. So that FW is the stress, that is the buckling strength of the web portion. Okay, so whether it is safe enough or not, that we can check it. Okay, so now the condition is, for safety condition, FW should be greater than V load. So V load is nothing but 241.5 kilometer. Okay, individually. Now we have calculated the FW value, that is buckling strength. Okay, buckling strength. So which is from page number 67, we can have the formula. Okay, V1 plus N1 into TW into FCD. Okay, so here B1 is nothing but bearing length. Bearing length that we are going to assume as 150 mm. Okay, and N1. So we you know that dispersion, it should be, it is like this. Okay, so here we can have flange. Okay, so the dispersion is going like this. So N1 is equal to, so the total H divided by 2 plus 2 times of thickness of flange. Okay, here channel flange we are going to take, since the dimension is very less when comparing with our I section flange. Okay, so H is equal to 600 divided by 2 plus 2 into thickness of flange, 7.6 mm. Excuse me. So N1 becomes 315.2 mm. So B1 value, N1 value, we have that. Then thickness of web is nothing but 11.2 mm. Sorry, here the thickness of web, we are going to take it as a channel sections web. Okay, now, which is nothing but 7.6 mm. Since that is very least value. Okay, so 7.6 mm we are going to take. So we need to calculate FCD value. So for this we need KL by R minimum value. Okay, so that KL by R is nothing but lambda W. So we have one formula, that is 2.45 into D1 by DW. Okay, so 2.45 into D is nothing but the depth of web portion alone. Okay, so 600 minus, okay, this is 21.3 mm, and here it is 7.6 mm. So the height from here to here it is 600 mm. Okay, and here we can have the projection like this. Okay, this height root radius is nothing but 70 mm. So that root radius you have to deduct it. So 600 minus 2 into 21.3. So these two along with that root radius we are going to deduct. Divided by thickness of web for this section is 11.2. So if we are going to do the lambda W is becomes 144.49. So I am going to say it is 115. Okay. Now the lambda value of 115, comma our Fy value of 250 Newton per mm squared and the buckling class C. Okay, we are going to refer table 9C of IS 800 2007 so that we can get the FCD value is equal to 89.15 Newton per mm square. Okay. Therefore, Fw is equal to, if I am going to substitute all these value, I am getting 315.2 kilonewton. Okay. So our condition is Fw should be greater than our wheel load. Okay. So the Fw value we are getting as some 315 kilonewton. Okay, which is greater than our wheel load. Hence, the section is safe in buckling resistance also. Okay. So hence safe. Next, step 13. Step 13, that is check for deflection. Check for deflection. Okay. So the del value should be less than capital delta. So we have permissible deflection value, that is L by for simply supported beam of Gantry Girder is equal to L by 500. Okay. So the del value I have to calculate. For that, like a moving load, we have to take the, this is wheel 1, this is wheel 2, the entire span is L. Okay, that is 8000 mm. Here it is, the spacing between the wheel loads is 3.5 meter, which is nothing but 3500 mm. Okay, so now with respect to this moving load, the formula of deflection is equal to WL cube divided by 6EI into 3A minus 4L minus A cube divided by L cube. Okay, whereas A is equal to, okay, uh, L minus C divided by 2. So this is our formula. Okay, and W, so L minus C is nothing but 8000 divided by 3500 divided by 2. It becomes 2250 mm. Okay, therefore the remaining unknown, A we got it, L is equal to 8000 mm. Okay, E is equal to 2 into 10 to the power 5 Newton per mm squared, and the I value, so IZ I am going to take. So IZ value is equal to, we already calculated in the step 6. Okay, so 135543 into 10 to the power 4 mm power 4. Then W is nothing but maximum static wheel load. Maximum static wheel load. So that I am going to take the total wheel load 241.5 divided by factor of safety 1.5. Okay. So if I am going to take it, I am getting the value of W is equal to 161 kilonewton. So if I am going to substitute all the things into this equation, I will get, that is delta is equal to 161 into 10 cube into 8,000 cube divided by WL cube divided by 628 E into I 1355 1355 okay, multiplied with 3 into A divided by L. So L is equal to 8,000 minus A cube divided by L cube. Here it is for A cube 2250 cube divided by L cube 8,000 cube. So if we are going to substitute this, the del value becomes 9.6 mm. So what about capital delta? That is 8,000 divided by 500. It becomes 16 mm. Therefore, small del should be less than capital delta, permissible limit. Hence, the gantry girder is safe in deflection also. Okay. So last step, that is step 14, design of connections. Okay. That is, I have I section. Okay. And the channel section. Okay, this I and the channel section I have to connect it properly with the help of weld at these junctions. Okay, at the flanges. So for that we have to do the design of connection. Here Q should be less than QD is the condition. So QD is nothing but design shear uh, capacity of weld, and Q is nothing but required shear capacity of weld. So Q is equal to the required shear capacity of weld. So we have the formula, that is V into A into Y bar divided by IZ. Whereas V is equal to maximum shear force, that is 377.34 kilonewton, and the area is equal to, here we have only channel section that we are going to connect it. Okay, so that channel section we are going to take. So area of channel section 4564 mm square. Then Y bar. So we already calculated that the centroid of the section is lies on 247.59 mm from the top compression flange. Okay. With respect to this, what is the height of the channel section that we are going to take it. So 247.59 minus 7.6, so that we can get 239.9 mm. So IZ value we have calculated that from the step 6, 10 to the power 4 mm power. So if I'm going to substitute all this formula, then I can get the Q value of 304.82 Newton per mm. Now I have to calculate the design shear capacity of weld. Okay, so QD is equal to Ks into Fu divided by root 3 into gamma ml. Okay, so we already know that we have to assume the size of weld. So we are going to assume size of weld as 3 mm. Therefore, K value we know that 0.7. So 0.7 into 3 into, so FU value you know that, okay, 410 Newton per mm square into root 3 into gamma ml. For site weld, the gamma ml value is equal to 1.5 from table 5. Okay. So if I'm going to substitute gamma ml is equal to 1.5, then I can get the value of QD is around 331.39 Newton per mm. Therefore, Q is less than QD. Okay. So the 3 mm weld is to be used to connect the I section flange with our channel section. Okay, which means here I can have I, so this is rolled I section. Okay, and here we are going to connect a channel section. So this section have 3 mm weld. So this is our design of gantry girder. Up to this, the entire steps have been covered. Thank you all.